All right, let's talk about some addition and subtraction circuits, as well as a multiplication circuit that I'll show later on. So let's dive into this addition subtraction circuit here. We have two inputs here, A and B. We have this control switch that can decipher whether 0, we are adding the two numbers together, or 1, we're subtracting A minus B. And that will all sum out over to Q, our output. So say if we have an input of 3 for A and an input for B, 4, and we leave this on addition, we will have 3 plus 4 equal to 7, which is correct. If we go ahead and turn this to 1, we will have 3 minus 4, which gives us our answer of -1. All right. Now, let's talk about the inputs a little bit. We have only 4 bits, and this is in signed binary as well. All right. So our range, to put it short, will be from -8 to +7. As you can see, if I try to insert a -9, we can't, but we can with -8. And if I try to insert, say, a +8, I can't, but I can do a +7. And that's because for signed binary, we can only be from a range of -2 to the power of n, which n is how many bits we have, all the way up to +2 to the power of n minus 1. So in our case, 4 bits minus 2 to the 4th power is -8. And for the positive, we have 2 to the 4th, which is 8 minus 1 is +7. So that is our range for that. Also, it should be noted that our range for our output, because it's also signed binary and only 4 bits, again, can only give us an output of -7 to +8. So say if we try to do 7 plus 4 here, which is going to be way over +8, that's going to be 11. This output is obviously not 11. This is -5. So as you can see, this has some drawbacks. We could spend some time trying to figure out how this makes sense to represent +11, but right now I have no idea how that works. All right, now this C out is a little interesting as well. For example, it could represent multiple things depending on how we're representing it, what we want from our output, all right? So for example, if it was unsigned binary, for example, it could represent the carry out to become the most significant bit, for example. It could also, like a bit extender, for example. For sign magnitude, it could represent the sign, whether it's 1 for negative or 0 for positive. Or for 2's complement, it's usually most of the time ignored, or I should say it's always ignored, because the carry out when performing addition, for example, for 2's complement, there is no carry out, or we always ignore the very last carry out, if that makes sense. Okay. And now this XOR gate is basically doing a lot of magic for us for this control switch here. And that's because, for example, I'll write some binary here. If we have an input of 0, 1, 0, 1, so that's 5, and we XOR it, exclusive OR it with 1, 1, 1, 1, that's what this sign extender is doing. If this is selected to subtraction mode, it is giving an input of 1 and then extending its sign, which is 1, up to 4 bits. So if we were to XOR this result of these two numbers together, what we'll get is 1 and a 1 would be 0. A 0 and a 1 would be 1. A 1 and a 1 would be 0. And a 0 and a 1 would be 1. So this would be our answer if we XORed these two inputs together. And as you can see, what we're getting is a complete complement of whatever our input was. And that's what this XOR gate is doing, is it's complementing whatever B's input is if we have it selected to 1. Okay? So let's go ahead and move on to the multiplier circuit. Okay, and I might need to zoom out for this one too. All right, so I'll go ahead and show you how this works. This is performing simple multiplication. Say if we have an input of 9 here, and B an input of 3, we should have an output of 27. All right. Now this is unsigned binary, so we can extend past 8 like we couldn't do in the subtraction circuit here, the addition and subtraction circuit, or I should say positive 7 and negative 8. All right, so the inputs we can represent with this, with 4 bits unsigned binary, is numbers 0 through 15. So I'll go ahead and just prove that to you. If we try to insert a 16, we can't. And if we try to go anything under, well, it's unsigned binary, so we can't do any negative numbers. So we can only go up to a maximum of 15. That is 0 through 15 once again. So as you can see, this is a very complicated circuit, but something I want to point out here is, let's take, for example, these outputs here, S0 through S3, all right? You could see S0 is going straight directly to one of the results for the output, all right? Now, S1 is being moved here to A0, S2 is being moved to S1, and S3 is being moved to A2 here. So as you can see, there is some shifting going on here, and that's correct. We instead of having to reroute these guys in such a way like this, we could have also used a shift right effect, something like this right here that we've built in a previous homework assignments. So if we were to build this physically, this would be very, very complicated. We would have to have an enormous amount of input switches, specifically 8 input switches. And then we would have to have 8 outputs as well, so 8 output lights. And for these multiplexers here and these adders here, we would have to build that physically using TTL chips. And just looking at let's see if I could find it, one of these mux 2 to 1s, we would have to do that 4 times with an AND gate, 2 AND gates, a NOT gate, an XOR gate. It just gets so complicated and will become so big, and it'll be just very difficult to do. So I'm very happy to build this whole entire circuit using just Logisim. So anyways, I believe that is all, and thank you for watching.